Okay, so the physics homework problems. I don't have your email addresses yet because you're not signed up for Blackboard. So if you want me to send you the the if you want me to send you the document with the physics homework problems, send me an email. You know what my email is, and then I'll respond with the thing attached. I asked Mrs. Kolb to help send me a list from last year, but she hasn't done that yet, so she may not have been able to figure it out, or she might have forgotten, or who knows what. You know, Ms. Kolb. Yeah, Mrs. Kolb used to be the biology teacher at James River. Did you know that? Do you know Mrs. Kolb? She teaches the biology and research class here, but she used to be the biology teacher. And back when she was here was when they used to have a class called marine biology. Did anybody know about that class that used to be at Allegheny High School? Yeah, they probably don't want you to know about that. So what it was a class for seniors, and you learned about marine biology, and then during your spring break, you got to go to the U.S. Virgin Islands in the Caribbean to do a uh, project. So you would count fish and other stuff. So my older daughter, Jennifer, wanted to go on it. And at the time, we thought it sounded just like what I would call a boondoggle. You know, that means just an excuse to get a vacation out of the whole thing. And a boyfriend was going, who's also now her husband. But so we didn't do it. We're like, that's expensive and blah 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 blah. And then when Heather came along 5 years later, we'd heard more about it and we just let her go. So Jennifer's always held that against us. She said that she's 30 something now. Yeah, you wouldn't let me go on that trip to the Virgin Islands. And then to make it even worse, Heather said, my younger daughter said, "Oh, it's so nice there. You ought to go to the U.S. Virgin Islands." So we went there one time, and we've been back 6 times. So anyway, that Mrs. Kolb was one of the people that arranged it. The other one was Miss DeGroot. So it was Miss DeGroot and Mrs. Kolb. So that was our first experience. Well, we didn't really know her that well at the time. We just knew there was the biology teacher from James River High School that did it. Okay, so yesterday we were looking at this one example of a function which simplifies down just to y equals x, except at x equals 1, where this function is undefined at x equals 1, or actually it's indeterminate, and whereas this function is defined for all real numbers. So this little thing, why are we showing it? And I said because when we come to the definition of the derivative in the second chapter, it'll end up being something like this. And the value that we want to know what the limit is for this function is at the value of x, or the limit where this thing is indeterminate. So you have to know how to figure out what the limit of an equation like this is at the point where the function is indeterminate. So so if I were to say what is the limit of x squared minus x over x minus 1 as x approaches, well, at any number besides x equals 0, it's defined, and so you just plug the number in. But at x equals 1. But at x equals 1, it's not defined. And it turns out that if you take the limit as x approaches 1 of the simplified expression, where you cancel out these two terms, that this limit, which is just the value of the function, which is y equals 1, is the limit for the original function that was indeterminate at that particular point. So we're canceling the thing out. It's okay to cancel it out. when you're finding the limit. When you're evaluating the function, you can't cancel it out because they're not exactly the simplified function and the original function are not the same because of that 1 point difference. But when it comes to the limit, you can cancel those common terms out and then just plug it in. Okay. So let's just look at, if you don't need to write all these down, just pay attention for right now. So, where are other cases what are other functions that either are indeterminate or undefined at some point in their domain? At that point, the limit may or may not exist. I mean, 99.9% of the time, if you plug the value of x in that you're trying to find the limit into the function, you'll get the limit. But there are a couple of other cases besides the case we just looked at, which was where the function was indeterminate. There's also the limit does not exist at vertical asymptotes. So for rational functions where the denominator goes to 0 and the numerator doesn't go to 0, the function is undefined at that point, at the point of the vertical asymptotes. So there the limit does not exist. Some of the trig functions, all the other ones except sine and cosine, there are points in their domain where the function is undefined, like the tangent is undefined at pi over 2 and 3 pi over 2 and multiples of that. The cotangent is undefined at 0, pi, 2 pi, 3 pi, 4, multiples of pi. The cosecant is undefined at pi over 2 and some other ones. Where's the other one here? The secant, actually the cosecant is undefined at 0 and the secant is undefined because you have vertical asymptotes when you look at these functions. If you remember back to the second semester pre-calculus and remember the graphs of those functions, we'll look at them in a second. Some other forms of trig functions besides just the base, just besides these simple functions. And also some functions that involve absolute values. These are examples, which I'm going to show you right now, of functions where the function doesn't exist at certain points, and therefore the limit does not exist. So what we looked at just a second ago was where the limit existed, but the function did not exist. These are types of functions where the function does not exist and that therefore the limit turns out to not exist as well. I'm going to skip over that for right now. We'll come back to that. This is a review of rational functions, but I'm going to... So, this is an example of a rational function. It has two vertical asymptotes. That's where the denominator, each term in the denominator goes to 0. So you have a vertical asymptote at x equals 4 and a vertical asymptote at x equals -1. And so if I asked you what the limit of that function was, so let's just write that down. If I said, what is the limit of the function above, I'm not going to rewrite it, as x approaches 4, so it's this value of x, I would say it does not exist. And the reason is because if I approach x equals 4 from the left side, the function goes to -infinity or approaches -infinity. If I approach x equals 4 from the right-hand side, the value of the function approaches +infinity. So they're not approaching the same number. For a limit to exist, they have to approach the same number. In this previous problem, when I came from the left-hand side, I approached 1, y equals 1, and when I approached the right-hand side, I also approached the same number. So the limit does exist there, but because I'm approaching, for two reasons. One is I'm approaching infinity, a -infinity, and also because it's not the same number, the limit does not exist at x equals, as x approaches 4. Now if I said, what is the limit of f of x as x approaches 3, in that case, I'm just looking at this. Here's x equals 3. So as I come from the left-hand side, the value of the function here is getting closer to 0. And if I come from the right-hand side, it's approaching 0. So it's approaching the same y value from both sides. And therefore, it's just simply the value of the function, which is 0. This is the value of the function. The only place it's weird is positive 4 and negative 1. So that's an example of a rational function and where the limit does not exist. Here's the tangent function. So, the tangent is the sine divided by the cosine. So when the divided by the cosine, when the cosine goes to 0, which is at pi over 2, the function goes to infinity. On the left-hand side, it goes to positive infinity, and on the right-hand side of the x equals pi over 2, it goes to negative infinity. So it's just like the rational function, except it's a trig function, but it has the same kind of asymptotic behavior. So if I said, what is the limit of the tangent of x as x approaches pi over 2, I would say that it does not exist. So that's what it means for a limit to not exist. That's how you look at it graphically. You see if the function approaches the same value. This is one that's another form of a trigonometric function. So it's the function is the sine of 1 over x. So what happens as x approaches 0, it's not that there's a vertical asymptote, but it starts to, because it's 1 over x, it starts to oscillate more quickly, and then it just keeps oscillating, and it doesn't exist at x equals 0. So the limit does not exist for this one. It exists at every other value of x except x equals 0. And then the case of the absolute value is you have the ratio of the absolute value of x minus 3 divided by x minus 3. So the way this function looks is that when x is greater than 3 over here, the numerator is positive, or the argument in the absolute value is positive, so it stays positive. So you have a positive number. So let's plug 5 in there. So you'd have 5 minus 3, which is positive 2. The absolute value of positive 2 is positive 2. And then the denominator would be 5 minus 3, which is positive 2. So the ratio is 1. And so for every value of x greater than x equals 3, this function is just 1. And then when x is negative or below negative 3, like say 2, you get a negative number here. But the absolute value makes it positive. So the numerator is positive. The denominator is negative, so the ratio is negative 1. And at x equals 3, the function is undefined, or actually it's indeterminate. You end up with 0 divided by 0. But this is a case where it's indeterminate, but the limit does not exist, because when you approach x equals 3 from the right-hand side, the value of the function approaches positive 1. And when you approach x equals 3 from the left-hand side, so here's the x value getting closer, and you'll notice the y value is always negative 1, so it doesn't approach the same value. So the limit in this case does not exist. So let's write that out. So what we would say is the limit as x approaches 3 of the absolute value of x minus 3 over x minus 3 does not exist. Okay, so those are the main cases of examples of functions where the limit does not exist. Okay, before we go on, so that's how you graphically evaluate limits. You look at the function, see what the function is doing around the value of x where you're taking the limit. If it's approaching the same value of y, then the limit exists. If you have vertical asymptotes, absolute values like this, then the limit does not exist because you're not approaching the same value. Now there's a couple of problems in the book, and I'm going to try to make one up here. You can use stepwise or piecewise functions. Does anybody remember what piecewise functions are? I don't really emphasize piecewise functions that much, but anybody want to make a guess? Yes.
They have little parts.
Right. Yeah, so they're usually like different functions stuck together, and you list them, and then you define your domain. So you might say from x equals negative infinity to negative 3, the function's this, and from negative 3 to something, it's this. And so I'm just going to make something up here. Actually, I'm going to get a piece of graph paper. Instead of using my drawing. So I need to delete. Usually to make people who try to make calculus hard like to do a lot of piecewise functions, but it really doesn't. It just makes some people confused. So I'm going to make up a piecewise function. So let's say we'll use a linear term here. So we're linear to here, and then we jump down there to another place like that. We will then have some kind of function that approaches a vertical asymptote right there. So let me draw a vertical asymptote. So somehow there's a vertical asymptote right there. And this thing comes down like that. And okay, so what we're seeing is we'll say from negative infinity to x equals negative 1, 2, 3, 4, 5, the function exists. Let me click over here for just a second. So if I asked you what the limit of this piecewise function was as x approaches negative 5, I would say the limit does not exist, because when I come from the left-hand side, I approach this value of y, and when I come from the right-hand side, I approach this value of y. So the limit does not exist at this point. The function does exist because I put a little dot up the top. Okay, so I probably should actually put little circles right here. So this is saying that the function does not equal this value at x equals negative 5. It equals this value. And this one is also a little open dot. Okay, now what I've got here is I'm going to have two empty little dots. So again, as x approaches negative 1, the limit does not exist. At any point from here to here, the function does exist, and therefore the limit would be the value of the function. In this case, the function does not exist at x equals negative 1 because I don't have a dot anywhere. It's not continuous, so there's this jump, but so that one, the function does exist. Here, the function does not exist, and the limit does not exist either. When we get to the vertical asymptote, the limit does not exist because coming from the left-hand side, the function approaches negative infinity, and approaching it from the right-hand side, it goes to positive infinity. It's not approaching the same value. Therefore, the limit does not exist here at x equals 3, and the function does not exist because you've got vertical asymptotes. You could put a dot here, and then the function would exist at that value of x if you wanted to make the function exist. And then finally, this part, this asymptote, at this point, the function does not exist, but the limit does exist, because when I come from the left-hand side, I approach this y value. When I come from the right-hand side, I approach that value. So that's kind of how these graphs of piecewise functions is you can make observations about whether the function exists or does not exist, and also whether so that means there is a value of y for a given value of x. That's what it means to exist. But to have a limit, the function either exists or doesn't exist. But the key thing there is that as you look at the graph coming from the left-hand side of the value of x and the right-hand side, that they approach the same y value. The function doesn't have to exist to have a limit, but they do have to approach the same value. Okay, so that's kind of how those go. Now, how do you do it numerically? So that's the second topic in this section. So it's pretty easy. All you do is you just pick values of x that gets closer and closer to the value of interest, and then you look at the y values, and if those y values are approaching in the table to the same value, then you say that's the limit. Okay, so it's just a matter of making up a table. I said I was going to use Excel here, so I guess I'll do that. And while I'm thinking about it, let me make sure I get everybody's attendance here. Oh, there's Christian. And I don't see Gage. Okay. So we were doing this in physics yesterday. I put all the data together, so I'm all ready for a physics lab. So what I'm going to do is I'm going to have a column that has x and a column that has f of x. So these are just labels. And what I was looking for was, what is the limit of this function as x approaches 2? Now, because it's a polynomial, the answer is going to be the value of the function. So this is just demonstrating the process. It's not going to be any great revelation or anything like that. It's just kind of how you do these things. And you could do it in a handwritten table, but I'm doing it in Excel. So what you would do is you'd pick values that get closer and closer to 2, but not equal to 2. So you don't ever put the value, when you're doing it numerically, you don't ever put the actual value in there, the x value that you're taking the limit as it approaches. And okay, so I'm just using the same increment. And so the function, the way you do functions in Excel is you put an equal sign, and then you, instead of putting x or something like that, the variable is in another cell. So that's x. X is the value in cell A2, and you square it. So you use a little hat, and you subtract 2 times. You could either enter A2, or you could click on the cell A2. And my memory's not doing too good today. +1. So there's the value of the function. So it's 0.81. And then what I can do is I can just copy this formula. So the way you can copy something is by clicking on the cell, going to the corner of the cell, and just dragging it down. Now, to do it down here, I could copy it, just Control C, and then just highlight where you want to copy it to, and use Control V. So what we see here is that the value of the function as you approach from the right-hand side, slightly greater than 2, is getting closer and closer to 1. It's not exactly equal to 1, but it's definitely getting closer. And then on the other side, the left-hand side, as you get closer and closer to 2, the value of the function approaches the same number, 1. And I could go even closer, but at some point you're like, okay, I get it. It's not going, there's no vertical asymptote. If there was a vertical asymptote, this thing would be growing instead of getting bigger instead of the change getting smaller. So that's how you do it numerically. It's a piece of cake. And then you observe. Okay. There's your homework for section 2. So some of it's doing it, probably 9 through 16 is doing them graphically. We're going to go back and do just a little review of rational functions after you copy those down. And what I'm doing here, if I remember my pen, hopefully I did. If not, I'm going to borrow one today. Oh, I got a pen. Okay. This is where I'm using my governor's school calendar. So hopefully you're doing the same thing. So I'm writing down when I assign these things. So this is due next Thursday. So if you forget to do it, hopefully I will remember to do it, and you can just come up and look at this if you need to know when something's due. I was going to do it on, be fancy and do it on the computer, but I seem to forget because I'll do that later, and then a note later it comes and I've forgotten to do it. So sometimes technology is not the answer to everything. Did everybody get that? Hopefully. Let's just do a little review here of this rational function thing. So I'm going to ask you questions, see how much you remember. So did you ever do one like this? How complicated did your rational functions get in pre-calculus? I like rational functions because they're easy to draw. If you do a polynomial, and the polynomial doesn't have any x-intercepts, it's really hard to draw because then you just have to start picking points. Anyway, we're going to do this anyway. Actually, that reminds me. See, in 20 years, all the people that are have these recollections of how things used to be are going to be either retired or dead. So I'm going to tell you. I was thinking, I think these are interesting things, but yeah, it's your experience. So how did people in 1970, 60s, and 70s plot functions? What do you guys do if you want to plot something? Use your graphing calculator, right? Is that what you do, right? When's the last time you actually plotted points on a graph and drew a line between them to kind of do that? Did you do that in pre-calculus at all?
Yeah, we had to do that for like drafting cosine and sine.
Sine and cosine, yeah. So, yeah, when I in the 70s, we did finally have calculators. But if you wanted to graph something, you still had to use graph paper. Okay, so engineers would actually take their notes on this green graph paper. I'll show it to you one day. And it was for two reasons. One is because it already had graphs on it, so if you wanted to do a graph, you already had graph paper. Secondly is it provided a nice structured form to write your equations out, so it was just better than just single ruled paper. But if I had this function I wouldn't be able to put it into my graphing calculator. I wouldn't be able to go to a computer because we didn't have computers then to plot it. So you'd have to actually plot sufficient points on a piece of paper. So let's just pretend I'm plotting some points here. And I wonder, I was thinking to myself, does it make students nowadays have a harder time visualizing things because they never had the experience of having to do this enough times? You plot something on a graphing calculator and you see this curve and you're thinking, oh yeah, but do you miss out on something? You don't have the. Okay, so let's say I've plotted the function and it looks something. These are the points that I get. So, one way of doing this would be to say, okay, I'm just going to freehand in what I think the function looks like. Okay? So that's okay, but it's not really that good. It's not good enough for scientific work. So once you plotted the points, you'd pick values of x, you'd plug it into your calculator, or even in the 60s, you'd probably do it by hand, or you'd use a slide rule, and you would plot sufficient points so you're like, okay, I have a pretty good idea of what this thing looks like. I've got enough points that I can plot it. Then what you would do is you would use these tools, which probably most people have not seen. I used to have them. I don't know if I still have them, some squirreled away somewhere in my attic. And they were called French curves. I don't know why. So you would have this, along with your rulers, you would have these curves. And you would put that on your graph paper and try, just manipulate it around so that the curve here matched what you thought the curve should look like based on my hand drawing, but you would actually have a much more, you just have something to guide your hand and it's not shaking all over the place, and it gives you, so you would use these French curves. I had a set of French curves in college, and I used those pretty much through the entire college if I had to plot a graph. So, the one advantage of doing that is, you think about, it's a function is just a bunch of dots that are, and then for every value of x, there's a value of y. In this case, you just plot enough values of x versus y so you can get an idea of what the curve looks like, and then you use those French curves to make it look nice. So that was, how many people have seen a French curve? Yeah, nobody. Okay. I'm a dinosaur. Okay, back to here. So do you remember what you had to do? What were the things you would normally do when you're plotting a rational function? You would find certain key things associated with this rational function, which I have factored it. So you would always if you can factor it, you'd factor it. Right. Okay. So what are the values of x where you have vertical asymptotes? Do you remember? Well, for this example, could you? Right. So it's where the factors in the denominator go to 0. Yeah. Now, if you had the same factor in the numerator and the denominator, which usually didn't happen, but that's what we're saying does happen in this case, there you don't have vertical asymptotes, you have a hole because it's undefined. Right? And then, so that's the significance of the factors in the denominator going to 0. What's the significance of the numbers in the numerator going to 0? So I'll ask somebody else. Anybody know what that means? Okay, so what is, if I set x equal to -2 in that function, what is the numerator equal to? 0, yeah. So that's the values of x where y is 0. Those are the x-intercepts. So that's what you use the numerator for. Then to find the y-intercept, the y-intercept is where what is equal to 0? X is equal to 0. So you plug x equal to 0 into your original non-factored form, and you see that the y-intercept would be 3/2 once you take -6 divided by -4. So that gives you the y-intercept. And then you have the horizontal asymptotes. Okay. So does anybody know what the y value, y equals what for the horizontal asymptote?
That's after you have canceled out the whole and did your vertical asymptotes, whatever's on top, whatever in the numerator and the denominator, you have to divide it or something like that. I can't remember exactly.
Yeah, we'll actually look at this again relative to calculus, but there are a couple of rules. One is you take the highest order terms in the original function, x squared and x squared, and if they're the same, you take the ratio of the leading coefficients. It's called leading coefficient test or something like that. So the coefficients are 1 and 1. So the horizontal asymptote would be y equals 1. And let's see what else. Uh, that's about it. So, so let's just let's write all that stuff down that we just said. So we have the vertical asymptotes. That's where x values where denominator is 0. In parentheses, and the numerator is not 0 at the same time. Okay, but we'll assume that. So in this case, it's when x minus 4 equals 0 or x equals 4, and when x plus 1 equals 0, which is x equals -1. So those are the lines for the vertical asymptotes. Okay, then you've got the x-intercepts. Now that's where y equals 0. So, or f of x equal to 0. So that's where the numerator is 0, meaning the values of x where the numerator is 0. So that's where x plus 2 equals 0, or x equals -2, and x minus 3 equals 0, or x equals 3. So those are my x values. The actual intercept would be -2, 0, and 3, 0. So those are my x-intercepts. Then you have your y-intercept. So that's where x equals 0. So there, what you do is you take your original function and you just have 0 squared minus 0 minus 6 divided by 0 squared minus 0 minus 4, which simplifies to 3/2. So it's y equal, well actually it's a point. So it's 0, 3/2. And then the horizontal asymptote what you do there is you take, there's a couple of rules that we'll learn, which you've probably seen before, but you take basically you take the leading coefficients in front of the x's, the highest order terms. If they're the same, then what's happening physically, mathematically what's happening is that if you look at the first expression before it's factored, as x gets large, the squared terms we say dominate, because 100 squared is 10,000, whereas minus 100, so you have 10,000 minus 100. So the first term is so much bigger And as you get x bigger and bigger and bigger, that first term becomes a larger percentage of the numerator and the denominator. And so that's why we, when we talk about horizontal asymptotes, that's when x either gets very large positive or large negative. That's why we only worry about the higher order terms. And so at that point, the x squared kind of cancel out, and you just get 1. So it's y equals 1 is the actual equation. So with that information, let's graph it. I do have the graph, but I've got too much junk on it, so I'm going to redo it here. So we can draw red lines for the vertical asymptotes, and they were at, I forgot already, let's go back here, 4, -1. So we draw a vertical line here at 4, -4, and at 1. The x-intercepts are at -2, 0, and 3, 0. And then you have a horizontal asymptote, and I typically draw those only outside of the vertical asymptotes because they really don't have much use inside and they just get confusing. So that's my those are my horizontal asymptotes. And the only thing I have left is my y-intercept, which was 3/2, which is about right there. So, you're going to come from this direction. Actually, that's bothering me. Let me go back here. I was thinking it would be on the top side, so let me think about this. Did I make any mistakes?
I think it's 4 and -1.
Is it?
Yes. So I think
You're right. Yeah. Okay. So the reason I knew something was wrong is because when you have x squared over x squared, you always come from the top. And like the way I plotted it, I had to come from the bottom because it couldn't cross this asymptote. And so I knew I did something wrong. So thank you for, I would have figured out in a second because I was like, something is wrong. Okay, so let's move this over here. We'll replot these things. So they're in the right place now. Sorry about that. Oops. We all make mistakes. The key thing is when you recognize your mistakes and you don't keep going. Okay. Okay, so everything else is okay. So now we can actually plot this correctly. So we're going to have a vertical asymptote here, and I know that it has to be on the positive side just because I have positive x squared over positive x squared, so it's going to be above 1. So it's going to look something like that. I might have to plot this more accurately, I might have picked an additional point greater than 4. Now, if you have a single 0 in the denominator where there's a vertical asymptote, that means that you go from positive infinity to the opposite. So I know it has to come from this direction just based on that, and also because just because of other stuff. Because if I come up here through this x-intercept, I know that it has to then go through this y-intercept, and then it's going to go all the way up to positive infinity. And because this again was a single root in the denominator, it has to come down here to negative infinity, which also agrees with the fact that I've got an x-intercept right here. So there are lots of little different things you can check once you get, if you ever get good at this, you've done enough of these. So anyway, so there's the rational function. That's what it looks like. It's actually a pretty decent representation because you got all these guides, these asymptotes, horizontal, vertical asymptotes. You've got the intercepts. So it gives you a lot of information to actually do a pretty decent plot. Okay, so that's my rational function review. So we're going to on to section 3 now. And let's see. So now we're getting into the good stuff. So now we're going to come up with techniques to evaluate limits analytically. And again, 99.9% of the time, you would just plug the value into the function. But there are 3 specific special cases that we'll need to know how to use when we get into chapter 2 to be able to come up with the derivatives for polynomials and for rational or radicals like the square roots of stuff, and also for trig functions. So we're just going to look at all 3 of those techniques, and they are let me put this on one page, so small. So as I just said, the limit can usually be evaluated by just evaluating the function at the point, as long as it's in the domain of the function. So polynomial functions, your default position is to just plug it in and see what you get. Now, if you get a number, then you're done. And I have this nice flow chart, which I'll hand out in a couple of days, which kind of show you the decision making you have to go through. But polynomials, there's no holes, there's no vertical asymptotes, so you just plug the x value into the function. Most trigonometric functions over most of their domain. Sine and cosine, there are no vertical asymptotes, there are no undefined regions, so there you're safe for any value of x. For the 4 that the 4 other trig functions, you just have to worry about where it goes to infinity. And rational functions, again, vertical asymptotes are where we, everywhere else, except for where you have vertical asymptote, you just evaluate the limit by plugging it into the function and getting the answer. Let's skip that for a second. I just want to talk about these techniques. So these are the 3 special techniques. One's called the dividing out technique, which we sort of used with that made-up function. If you have a polynomial in the numerator and a polynomial in the denominator, and there is some value of x where both the numerator and the denominator go to 0, you can just cancel out those factors, and then the resulting function, which is defined for all values of x, you can just plug the number back into that one and get the limit. So that's used for where we factor stuff. The second one is called rationalization, and that is where we have a square root of something. So that's how we handle square roots. And the third one is for trig functions. It's called the squeeze theorem. And each one of these techniques will be used in chapter 2 to come up with equations or procedures for calculating the derivatives of most functions that we are interested in, or we can use, and the information that we glean from using these techniques, we can then use other properties of derivatives to find the derivative of pretty much any function we need. So we're going to talk about the dividing out technique first. So what does it say? These will be useful in finding the derivative of different functions in subsequent chapters. These are used when the expression is indeterminate. Okay, so what does indeterminate mean? Well, here's another example. It's not exactly the same one that we looked at before, but so let me write it out on this page here. So I think f of x equals x cubed minus 1. So if I said, what is the limit of f of x as x approaches 1? And you'd say, well, it's a rational function, and you said most of the time you can just plug the number in. So I do that. And at x equals 1, I get this result. I get 0 over 0, which is indeterminate. So that's indeterminate, okay? That's one example of indeterminate. There are other indeterminates. You could do infinity over infinity. You could have 0 times infinity. You could have 0 to the infinite power, something like that. So it usually involves the ratio of the same or really big things or zeros, or multiplying 0 times infinity. And ultimately, I guess you can always come back to, well, except for this one, you can come back to 0 because infinity is 1 over 0. So if you replace this with 1 over 0, you'd have 0 over 0, which is back to the original indeterminacy. For our cases, it'll always be in this form until we get to chapter 9. So for the most part, it'll be easy to recognize the indeterminacy. You'll say, okay, I'm going to plug the number into the function. I get 0 over 0. Hey, I need to do something. There's probably the limit still does exist. It's just I have to do some additional work to be able to figure that out. So, and if you plot this graph, x cubed minus 1 over x minus 1, it looks just like this polynomial, except there's a hole right here at x equals 1, y equals 3. So graphically, I would know the limit is 3. To do it analytically, what I would do is I would factor the numerator into the denominator. And I think this is x minus 1 times x squared plus x plus 1 over x minus 1. We can figure that out. Let's do that. Here's another review. Long division. So 1, 0, 0, negative 1. If I'm going to divide this, if I'm going to factor it out, I need this factor. So I'm just confirming that this is actually what the result is. So I would put this is a factor x minus 1, but it's this 0 is x equals 1. So I'm going to put 1, not negative 1 in there. So you bring this down. 1 times 1 is 1. 0 plus 1 is 1. 1 times 1 is 1. 0 plus 1 is 1. 1 times 1 is 1. Negative 1 plus positive 1 is 0. So there's a 0 remainder in my synthetic division, and what I have left over is these three numbers. So it is actually x squared plus x plus 1 is what you would have if you factored x cubed minus 1 into two terms. You've got a real term, which is x minus 1, and you've got the other one you can't factor anymore. You'd have complex roots to that equation. So you can see it does have a common factor, and it always has to have a common factor because that's why it's indeterminate. So this observation would lead me to believe that I have to have a factor x minus 1 in that original x cubed minus 1. Otherwise, it wouldn't cancel out. So the canceling, or the I always forget what they call this. You think after 8 years I'd remember. Dividing out technique. I want to call it the canceling out technique. They call it the dividing out technique. So after you've factored this, that's the whole idea behind the canceling dividing out technique. See, I can't still say it wrong. What you do is you simplify that down by dividing out the common factor, and then you take the limit not of the original function but of this simplified function, which doesn't have any indeterminacy to it, as x approaches 1. So you plug it in there and you get 1 squared plus 1, which is equal to 3. which is what we saw in the graph. So the limit is 3. So what we'll do is I'll do another example, then I'll have you work through an example. We'll do that tomorrow. I've got to get on the road and head on over to Rockbridge for something right now, so we're gonna stop 5 minutes early.